with homework questions, and we're going to have to keep the time brief. We've got a lot to get through. 25, in what section?
That's not assigned.
Okay. That was a view. And I'm going to take this, when I answer questions, I kind of like to take a break from this overhead and do it in real time with you guys. So, this is number 25 and number 25. All right, so we got x squared plus 1 dy dx. Plus 3x cubed y. Make sure I get the right one. 3x cubed y equals 6x. And when they write, I don't know why, sometimes they actually use exponential notation, e to the power like a number 3, and then down here, exp. That's oftentimes computer like syntax, but it's just for the function, the exponential function e to the negative 3 halves x squared with the initial condition y of 0 equals 1. Okay. All right, so this is about linear first order, so we're looking at sort of transforming this until we recognize that it's linear first order. Let's see, if we start off by dividing, just divide through by the x squared plus 1. Is that right? Okay. Yes, I remember this one. Now, this is linear. Doesn't look very linear, right? But when they say linear first order, it's linear in y. dy dx plus some function of y equals just some function of x. So there's a y to the first and nothing over here, no dependent variables. So this would be in our formulation for that. That's our p of x. This giant piece of business here is the q of x in that. Okay? And what it says to do is use an integrating factor that we are calling rho of x, and it's going to be e to the p of x, and we want to do that. 1 plus x squared dx. Okay? How do you handle that?
Is there no way to reduce that?
There might be, yeah, it looks like there might be a tan inverse lurking in there, or maybe a tangent, but here's the thing, this is an improper rational expression. The order of the top, or the degree, is larger than the degree of the bottom.
You need line division?
Yes. Polynomial long division.
I love that.
It's not that hard.
Actually, yeah.
But they don't teach this much anymore. It's kind of fallen by the wayside, a little obsolete until you get to here. And we're dividing 3x cubed by 1 plus x squared. So 1 plus x squared into 3x cubed. And I just go ahead and fill in the missing terms. 0x plus 0, whatever. Now, the way to do polynomial long division is much like numerical long division, except I'm matching powers of x. How many x squares will go into 3x cubed? 3x. And then you take that number and multiply by the original divisor, and we get 3x cubed right there. That matches up. Plus, now be careful, 3x times 1 is 3x. I line up my like terms. I got 0 there. And then the error term, how close did we get? Subtract that from the original. There's a 0, there's a 0, and we get 0 minus 3x, so that's negative 3x, right? And that's what's called our remainder. So it could literally, this function could be a whole term 3x minus my remainder term 3x over 1 plus x squared. Okay? So our this becomes 3x minus 3x over 1 plus x squared dx. Just gonna leave that off. All right, now when we integrate this, we get, what, x cubed over 2? 3x squared, oops, sorry, 3x squared over 2. That's starting to look nice. I got an e to the negative 3x squared over 2 somewhere. And this is going to be what? It's a u substitution. So it's close to an inverse tangent because you got the 1 plus x squared downstairs, but you got a linear term, a linear factor up front. That would be 3 arctangent x. But I got a 3x in there, which more or less matches up with the derivative of the bottom, 1 plus x squared. So it's going to be a natural log, 1 plus x squared, but it needs to have a 3 when I derive it, so is it 3 halves? So that would be 1 over 1 plus x squared times 2x. The 2 would cancel that 2 and give me 3x. Yeah, that's it. Okay, a little more. Let's massage this around a little bit. This is going to be e to the 3x squared over 2, and I could write this as times e to the negative 3 halves natural log 1 plus x squared. Yeah. Right. But log properties, this guy in the front can be thought of as a power on that. So it's e to the natural log 1 plus x squared to the negative 3 halves. So that factor, that part of it, this is e to the 3x squared over 2. And e to the natural log, I love that. That's why I want to use that as a power, because e and natural log are inverses. And I get 1 plus x squared to the negative 3 halves. Right? Obvious. Obvious. All right, now that's our integrating factor. Okay. This is, good God, this is why I gotta wake up early and do you guys' homework problems. Okay, so what do we do with that? Yeah, we multiply in this form, and I'm just going to call that star for a moment. We multiply in this form. We multiply both sides of the equation by the integrating factor. And so what that's going to look like is e to the 3 halves x squared, and someone had a good question last time. I know that when I multiply that to the left side, that represents the derivative of some function. E to the 3x squared, or 3 halves x squared, times 1 plus x squared to the negative 3 halves dy dx. And once we put this together on the left side, it's going to be the result of differentiating some function via the product rule. Okay, so plus, then we got the 3x cubed over 1 plus x squared. These aren't the easiest ones. Okay. Times y equals, and what happens when I multiply the right side? Look at, I got e to the negative 3 halves x squared. I'm going to be multiplying e to the positive 3 halves x squared. What do those do? They cancel to 1. Yeah, because they're inverses of each other. If you add their exponents, yeah, you just get to 0, e to the 0. So imagine you get e to the, when you multiply this factor, 3 halves x squared, those add to 0.
Hey, e to the 3x squared over 2 missing from the second piece of...
Oh, right. There's that, and I forgot to multiply that business.
That's what I get.
X squared to the negative 3 halves equals, and on the right side, those are going to cancel each other out. I'm going to have 6x x squared plus 1. And it's going to be times, and I got 1 plus x squared to the negative 3 halves, right? Now, the good thing is, the denominators are going to match up on some of those, 1 plus x squared.
But if it's the negative 3 halves, it's...
Oh yeah, there's another 1 plus x squared. Okay, so cleaning this up one more time. E to the 3 halves x squared, 1 plus x squared to the negative 3 halves dy dx, plus, now careful, this is a power 1 in the denominator. I have a 1 plus x squared to the negative 3 halves in the numerator. Okay, imagine this guy on top of that, and I subtract the coefficient, or the powers. It would be negative 3 halves minus 1 to get those together. And I'd have the 3x squared, 3x cubed. And I don't know, yeah, and it's going to be 1 plus x squared to the negative 5 halves. Okay, equals, and on the right side, same thing, negative 3 halves minus that 1, because they're the same factors. This is 6x, x squared plus 1 to the negative 5 halves as well. Yeah. Okay. Now clearly, this is the derivative of e to the 3 halves x squared, 1 plus x squared to the negative 3 halves. That would require, that's the dy dx. Oh no, it's the derivative of this. Let's see, that's the dy dx. That's the derivative. Right. You get the 3x, and the derivative of this, 2x. This is the form. If you took a half hour or 20 minutes to check this, this is the derivative with respect to x of e to the 3 halves x squared, 1 plus x squared to the negative 3 halves, y. Derivative with respect to x. Okay, product rule on this part, you'll see that anyway, I'm hoping that's true. That's what we want. And this is just 6x, x squared plus 1 to the negative 5 halves. Okay, then at that point is when you can think about multiplying both sides by dx and integrating. This is a derivative, so if I take the antiderivative of it, then we get e to the 3 halves x squared, 1 plus x squared to the negative 3 halves y, equals, how do I integrate this? You can do a substitution.
U equal x squared plus
Mhm.
1, du equal to dx.
2x dx, but I got a 6x dx, so how about this?
You equal out to 6, yeah.
I'm going to leave the 2 in there because now that matches up with the du. So we got 3, and this is u to the negative 5 halves, 2x dx, that's du. All right, so using the product rule on this, integral of u to the negative 5 halves, bump up the power by 1, u to the, add 2 halves, so that's negative 3 halves, divide by that negative 3 halves, but that's equivalent to multiplying by 2/3. Luckily those cancel out, and it's negative,
So 6.
plus c. And this is going to be negative 2u to the negative 3 halves plus some constant, and then divide by the rest of it. Now, notice when you divide by 1 plus x squared to the negative 3 halves on both sides, what happens? I got an x squared to the negative 3 halves all of a sudden. Yeah, they're going to be a form of 1 when I divide.
Well, aren't you also dividing by the c by the same thing though?
Yes.
Yes.
So this.
Yes. So the c will take that.
Okay.
So it's going to be, maybe I should write that down, but we're going to have, let's just do this. Let's do it in 2 steps. E to the 3 halves x squared y equals, and this is going to be negative 2 plus c divided by 1 plus x squared to the negative 3 halves. But if I bringing that power up, it's going to be 1 plus x squared to the 3 halves. Right? Because I was dividing by 1 plus x squared to the negative 3 halves, flip that back up. Okay, so, and by the way, dividing by e to the negative 3x squared, 3 halves x squared is the same thing as multiplying both sides by e to the negative 3 halves x squared. So do that to both sides. Yeah. I'm going to write it this way. C 1 plus x squared to the 3 halves minus 2 times e to the negative 3 halves x squared. Now we can handle the initial condition. And what was it? Y of 0 equals 1. So putting in 0, this is kind of nice. When I put, there's about a 1 in 5 chance that this is all correct, but what are you going to do? Y of 0, if I put 0 in for x, what do we get? Yeah, we get c times 1 minus 2 times e to the 0, and that equals 1. So that goes away. I get c minus 2 equals 1, so c has to be 3. So y of x equals 3, 1 plus x squared to the 3 halves minus 2 times e to the, wherever you want to put that, negative 3 halves x squared.
That's right.
Okay. Jeez. All right. Not the type of thing I put on a quiz. Okay.
But on the test?
Probably not.
Is it normal to,
Unless it was a take home.
I mean, you guys on your homework.
I feel that same way as you though, where it's
Wait,
like,
on the homework list?
Yeah.
That's fair game. I could, those are practice. You could put, I could put them on the homework list. All the ones I collect for problem sets, I do those problems first, vet them, and make sure. Okay. All right. I think that takes a lot of our time for.
it's normal to go through this and feel like you think you might have made an algebra error somewhere.
Yeah.
Like,
That's what usually happens. I mean, hey, everybody's human, so I usually give myself some odds at the end of it based on the difficulty. I give myself a 1 in 5.
I'm not gonna ask you to go through another problem like that, but in a couple of ones for Corinthians 2:25, the integrating finding row of x, I've turned out an absolute value of x or something sort of in the middle of an equation. I'm wondering how much does that need to be like?
Yeah, sometimes it seems like they do just discard absolute values.
Because if you discard it, you can just throw it into an x, but if you're having like,
yeah.
e to the absolute value of sine x.
Yeah, if you discard it, put it this way, just, if you discard absolute values, make a little note, assuming x is greater than 0.
plus it changes from 1 in 5 to 1 in 6.
Well, hey, under that
That's some
assumption. All right. So let's pick up where we left off last time. So we had talked about 1.5 and did some examples. And today we're going to be talking about various substitution methods.
Are you writing on the screen?
Okay. So there's various substitution methods, and this is 1.6. So just wrote them down last time. So we'll be handling, just to give you a synopsis of the 3 types of things we're going to be looking at. Equations of the form dy dx equals f, and not just f of x, that would be integral. But if we happen to have a form where we have some function of y over x, this is called homogeneous. Okay, I don't know why they call it homogeneous, because y and x, they're different. It should be heterogeneous. But that's reserved for something else. dy dx plus, now this looks a lot like linear, right? If I have some function of x times y equals some other function of x only, that would be linear. Now, if there is a power of y after that, that's the dependent variable, it's no longer linear in y if n is other than 0 or 1. This is called a Bernoulli equation.
Is this the same guy or part of the plan?
Part of the plan, I don't know, well, they're all related.
Yeah.
It's like a big Duck Dynasty, except for math guys.
Math dynasty?
It's all so that's a Bernoulli equation. There's Daniel, Jacob, the other ones. But one thing to notice, well, we'll talk about this when we come to it. That's a Bernoulli equation. Also, what we'll talk about is we'll do an example of a reducible, our first foray into second order differential equation, reducible second order differential equation. Okay? So first we're going to start off with, homogeneous. And let's just look at some examples. Okay. So first example, I'm just going to put Roman numerals on these guys. Say 2x, y prime equals x squared plus 2y squared. Okay. Now, this looks like a jumble. They often do. If you divide both sides, and I'm just going to leave the 2 on the left for a moment. If you divide both sides by the xy, then we get something that looks like 2y prime equals, and if I divide each term, x squared over xy, one of the x's will cancel, I'll have x over y, plus that 2, and then I'm going to have the y's cancel, and that's going to be y over x, right? Okay. All right, so at this point, we should be convinced that this is not separable. I can't factor and get those x's into one factor and the y's into another factor, so this is not separable. Can't resort to the methods in, 1.4. And it's also not linear. I got this y in the denominator. Okay. So we're out of luck with those methods. We need something else. One more step. If I wrote this down in the bottom as the denominator, I could write this as, 1 over y over x, right? And this is 2 times y over x. So this is a function of y over x, if that were a separate variable. Okay? So what we can do is, let's start a new page, is we could, this is going to be like a change of variables. This is our approach. We're going to let v equals y over x. Okay? Then those would both be v's. So we're going to transform it into an equation involving a different variable. Okay? But we got to keep track of some things first. If that's the case, then y, if I multiply both sides by x, y equals xv or vx. And then the derivative of that with respect to x, and I want to do that because my original problem involves a dy dx. So I want to know what dy dx is in terms of x and v. But if I go through the product rule, right, it would be derivative of the first times the second, and derivative of x with respect to x is just 1. So I get 1 times v plus the first times the derivative of the second, and that's dv dx. Okay? So I could just write the derivative of y, I could write that as v plus x dy dx. Okay? So my original equation, well, not original, but right here, and by the way, I'm just going to...
dy dx or dv dx?
Yeah.
Oops, that is a v. Good eye. That's a dv dx. I'm going to name that equation right there star. Now, what I'm going to do is I'm going to replace the y prime with its equivalent, and I'm going to replace the y over x with v. So that equation up there becomes, I'm going to replace, it was 2 y prime is v plus x dv dx. V plus x dv dx. Okay, equals, that's 1 over v plus 2v. Okay, so we're transforming this equation into one involving dv dx and v. Multiplying this through, oh, nice. Okay, multiplying this through, we get 2v plus 2x v dx equals 1 over v plus 2v. Yeah. All right, so on the right and left side, notice I could, those two v's will knock each other out, yeah? Subtracting 2v from each side. Okay. And then, we could divide by, I think we could divide by 2x. Well, let's just write this out one more time. We'd have 2x dv dx equals 1 over v, or v to the negative 1, however you want to view that. And so this is the same thing, we just transformed the variable, okay? It's just like the u substitution, and we got to keep track of the dy dx though when we do that. So we've transformed it into an equation, dv dx, and this is simpler, in fact, separable. So what we've done is we've transformed it into an equation that is now separable. Okay, so separating these variables, what's it going to look like? Divide by 2x, get the dx to the other side. I think v, goodness. Imagine multiplying both sides by v and dividing by 2x. I'd have v dv dx over 2x. All done with multiplication, so, you know, oops. Good God. This is the problem with pen, but it does look better. So we got, what was it, v equals, we got dx over 2x. Okay. So then, yeah, if you prefer, and I sometimes do, I don't like my dx's up top. You could write it as 1 over 2x dx, but then we integrate both sides because we were able to separate those variables to their respective sides of the equation. Okay, so we get v squared over 2 equals, and what is this?
1/2 that, right, 2x.
1/2 natural log 2x.